video, we're going to look at relations and functions. So a relation is really anything that relates two different quantities or variables. Hard to define without the word. It's a relationship between two quantities or variables. It's usually expressed in math as an equation. So for example, y equals 5x minus 2. That's a relation. X squared equals y. That's a relation. There's all kinds of relations. Those are just two typical examples in terms of equations. The set of input values is called the domain. Okay, the domain is, in other words, the set of all x's usually. The x's that can be input. Okay, that's not a formal way to say it, but it's the x's that you can use, that you can plug in. If for some reason there's an x that you cannot plug in, it would not be in your domain, and we'll see that soon. The set of output values, that's called the range, typically your y's. So x's on domain, y's, those are your range. It's the set of output values given your equation. Okay. So for example, this is a simple relation. There's no equation here, but it is a relation between two quantities, year and the price or rate of a first-class stamp. So in the year 1900, the price of a stamp was 2 cents, and in 1920 it was still 2 cents. In 1940 it cost 3 cents, and then it goes up in 1960 4 cents, 1980 15 cents, and then 2000 is 33 cents. And now I've quite frankly lost track of what it is. Okay. First, let's look at the set of ordered pairs. Okay. This is an ordered pair right here. When x is 1900, let's call that x, and when y is 2. So the pair 1900, comma 2, that is an ordered pair for this relation. It's typical because we're listing a set to put it inside of curly braces. So we have curly braces, and then the coordinate point, that's this point right here, inside of parentheses in the curly braces. Then we put a comma between the list of all of the ordered points. So there's commas inside the parentheses, which are to indicate the x, comma, the y, and then a comma between each ordered pair. So in this one we have 6 ordered pairs. Okay, and then we want to close the set with that curly brace there. The domain, that's the set of input values. Okay, in this case, the input values are 1900, 1920, 1940, 60, 80, and 2000. And that's it. There are no other input values in between 1900 and 2000. So we would have to explicitly list them out because, for example, the year 1910 is not an input value, so we can't just say x between 1900 and 1920. We really have to list them out. The domain, the x's that are input in the relation, and the range is the y's that are output. So I see a y of 2, a y of, there's 2 2's, but we only list it once, a y of 3, 4, 15, and 33. So it would be incorrect to say this, to say that the domain is x between 1900 and 2000, because that implies not only that x could be 1901, 1902, or whatever, but also that x could be any real number in between 1900 and 2000. So this implies x could be 1901.5 or something of that nature. And in this next example, we're actually given a graph. Okay, it's got some points on it. They're not connected like a line. So because these are discrete points, there's a finite countable number of them. In order to write the domain, which you can just call capital D, we'll have to explicitly list the x values that have a point. So the lowest x value is right here for that point, which corresponds to x equaling -2. The next x value is -1, 0, 1, 2, and the last x value is at 3. So we'll have to list them out, -2, -1, 0, 1, 2, and 3. And the range is the y value. So I'm looking at the y-axis now. The lowest y value I see is down here, which is at -3. And then I'm going to go up along the y-axis. So I have one at -3. The next y value is at -2. And at -1, 0, 1, and 2. That's a domain and range, or how you can find them given a graph. A relation in which the first coordinate is never repeated is called a function. It's a special type of relation. It's very commonly used in math. So it's called a function. A function is a relation in which the first coordinate is never repeated. Another more common way of stating it is that for each x, or for each input, there is, and you could add in the domain, for each x in the domain, there is exactly one corresponding y value. Okay, so first we're going to look at how to determine whether or not a relation is a function. Anything can be a relation, okay? Any way that you relate to quantities is a relation, but only certain relations are functions, not all of them. So is this relation a function? For each different x, there is only one y. So it's implied here that in the relation between size, shoe size, and price, size is the independent variable, or the x, and that price is the dependent variable. Now, no matter what shoe size you have, the price remains the same. If your shoe size or x is 7, the price is 35. When x is 8, y is 35, and when x is 9, y is 35. So for each separate x, there is exactly one y. So yes, this one is a function, and that's a shorthand abbreviation for function right there. Even though the y value of 35 is repeated multiple times, that doesn't matter because it's a y value, as long as the x's are never repeated, the first coordinate. Okay, this one, let's see, when x is 1, y is 5, when x is 2, y is 6, when x is 3, y is 7, so far so good. When x is -1, y is 6, when x is -2, y is 5, still good so far. Oops, when x is 3, y is 2. And here's the problem. We have two of the same x values with different y values. Now, if they had both said 3, 7, 3, 7, or they both said 3, 2, 3, 2, it would still be a function. You would just be unnecessarily repeating a point. But we have two of the same x's, when x is 3, and two different y values. So this is not a function. And next, the relation from last name to social security number. So that means, this implies that last name is the independent variable and social security number is the dependent variable. So for each and every last name is there a different social security number. Okay, now what is true is that no one has the same social security number, at least theoretically, right? We're not counting theft here and all that. Okay, so theoretically, each individual person has a different social security number. But there are many people with the same last name. For example, my last name is pretty common, Nichols. My social security number might be 001-24-5318 or something. I'm making this up. Somebody else with the same last name, let's say Jim, might have the social security number 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have the same last name, the same input, the same X, and two different Ys. two different outputs. So this is not a function. If you are presented with a graph of a relation, you can eyeball it and kind of tell if it's a function or not by using what's called the vertical line test. In the vertical line test, you imagine a vertical bar, like this, a vertical line, and you imagine it, like imagine a ruler, okay, moving it across the graph from left to right. So you don't actually have multiple lines. I don't have a good way to, well, actually, maybe I can move this. Let's see. Oh, I do have a good way. Here we go. So we're going to move this line across, and this one right here is actually not a function because, because for right here we're touching 2 points at the same time. So right there we have the same x and two different y values at that single x value. So because it's touching 2 points at once, this one is not a function. Okay. Let's do another vertical line on the next one. Imagine a vertical line, and you move it across from left to right. Let's try this again. There we go. I'm only touching 1 point at a time. And that's because for each x, we have exactly one y. So that one is a function. Okay, and let's just take the same little vertical bar over here. Whoa. There we go. Okay, moving it across, I'm only touching 1 point at a time. So for each x, there is exactly one y. For each x in the domain, there's one y, so that is a function. And then in the last one here, now these x's out here are not in the domain because there's no graph there. Okay, so this is fine. They're not in the domain, so they don't really count. Now over here, these x's are in the domain, and as you can see right there, when we're hitting 2 points at once, so this one is not a function. Okay, if something is a function, you can use what's called function notation to describe it if it's given by an equation and if you can solve for the y. So some sets of ordered pairs can be described by using an equation, and when the set of ordered pairs described by an equation satisfies the definition of a function, the equation can be written in function notation. For example, f of x equals, let's use this example right here, 5x plus 3. That really means the same thing as y equals 5x plus 3. And you read this f of x. The parentheses here are nice. They indicate the independent variable. Whatever goes inside those parentheses is the independent variable. And then whatever it's equal to is your y, or your output. Okay, and the function f of x equals 5x plus 3 is the same graph, it's the same function described by y equals 5x plus 3. One way of looking at this is that both of those are the same set of ordered pairs, x, comma, 5x plus 3. Now, it's not a common way of writing it, but that is one way to look at it, where this is the x and this is the y. Now, once you have function notation, it becomes very useful because you can describe, for example, f of 0 in a more compact notation, and that means what is y when x is 0, okay? So what you do is you replace this x right here by whatever's in these parentheses right here. So f of 0 equals 7 minus 2 times 0, because we are plugging in 0 for x, okay, which in this case is 7. Or f of 1/2 would be 7 minus 2 times a half. 2 times a half is 1. 7 minus 1 is 6. So what this means is that when x is 0, y is 7. So the more compact way of saying it here is f of 0 equals 7. And that's how you can say in a single compact way that when x is 0, y is 7. Okay, or when x is a half, y is 6. Okay, let's read off or find some function values given a graph. Okay, so this is a graph of a function. We're assuming f of x. For the graph shown, find f of 0 and f of negative 2. So this means when x is 0, we want y. What is y when x is 0? Well, this is our x-axis, so we come over here to x is 0, and then on up to the function, looks like 4. So f of 0 equals 4. F of negative 2 means what is y when x is negative 2? That's here, and then we go up to the function. So f of negative 2 is equal to this y value, which is positive 2. So y on the graph when x is negative 2. Okay, if you're given an equation, you simply find the y values by plugging them in. So let's begin by finding f of 2. That means we're going to replace each x by a 2. So we'll have 2 squared minus 3 times 2 squared, that's that x squared, minus 3 times 2. I prefer to put it in parentheses. That implies multiplication there. Plus 2. So it's 4 minus 3 times 2 is 6, plus 2. 4 minus 2 is negative 2, plus 6 is 0. So f of 2 is 0. F of bird, now this is silly, but there's a reason why I'm doing it. Essentially what you do, no matter what is inside these parentheses here, you replace each x in this function definition by whatever is in those parentheses. So f of bird, as silly as that is, would be, let's put it in parentheses, bird squared minus 3 times this x is bird plus 2. Okay? Makes no mathematical sense, but the point is, whatever's inside this parenthesis, you replace all of this variable, in this case x, with whatever that is, in parentheses. And it's important, if it's not just a simple number 2, to put it inside of parentheses for each of these variables up here. Okay? Get rid of that here. There we go. So now let's try f of negative x. So I'm going to replace this x and this x by negative x in parentheses, to be careful. So x squared will become negative x in parentheses, squared, minus 3 times negative x plus 2. After you write it out with parentheses, then we can simplify. So negative x times negative x is positive x squared, because the negative times the negative, that cancels, becomes positive 1. Then negative 3 times negative x becomes positive 3x, and that becomes positive 2. Okay, f of x plus 3. This is going to be useful very soon, this skill. So what that means is replace this x, or each x in here, by x plus 3 in parentheses. So x squared becomes parentheses x plus 3 squared. Then minus 3x becomes minus 3 parentheses x plus 3 plus 2. And then we can expand this out. So x plus 3 all squared means x plus 3 times itself, x plus 3. And if you're rusty, you'll want to write that out. We can go ahead and distribute that negative 3 to get negative 3x minus 9, and then the plus 2 just carries along. So in order to simplify this, we would need to FOIL. Okay, we have two binomials being multiplied. It's a binomial because each factor here has two terms, 1, 2, 1, 2. So FOIL stands for first, outside, inside, last. So we're going to multiply the first two terms. That's x times x is x squared. The outside term is x times positive 3 is positive 3x. Then I for inside terms here is positive 3 times x is positive 3x. And L for last is 3 times 3 is positive 9. This minus 3x carries along. And let's simplify these two as we go. Negative 9 plus 2 is negative 7. And then let's look for anything that simplifies here. Let's see. Positive 3x minus 3x cancels. I only have one x squared term, so I'll just rewrite that, x squared. Then I have plus 3x, that's all that's left. and then 9 minus 7 is positive 2, which is complete coincidence that it is the same as this. Random chance there. Okay, and lastly, let's find f of x plus h. That becomes useful in calculus. So we're going to replace each of these x's by x plus h. Okay, so x squared will become parentheses x plus h all squared. Minus 3x becomes minus 3 parentheses x plus h. And then the plus 2 carries along. Now we want to simplify that. So again, I'm going to write this out twice here, just to make it easier on myself. So you can skip this step. So x plus h times x plus h. Minus 3 times x plus h. Let's distribute the minus 3. So it becomes minus 3x minus 3h. And then this plus 2 carries along. So here I'm going to, again, have to FOIL. So my first two terms are x and x, which multiplies to x squared. My outside term is x times h is positive xh. My inside terms are, again, x and h, so positive xh, and then plus h squared. Then all these three terms carry along. Copy them, minus 3x minus 3h plus 2. And here and now I'm looking for anything that simplifies, and it looks like all I can do is add those two terms which are the same. xh plus xh is 2xh. So x squared plus 2xh plus h squared. None of these are like terms, so they can't combine or simplify at all. So that would be the final answer for f of x plus h, fully simplified. Next, let's look at domain and range of functions from graphs. If you are given a graph of a function, you can read off the domain and range the same way you would from a relation. So what we do is we're going to look at the x-axis here. As we go from left to right, there's nothing, nothing, nothing. These x's are not in the domain. My first x is here at x equals negative 2. So my domain here is going to start at negative 2, and I have a continuous line. So it's all the real numbers from negative 2 up to this x right here, which is 1. Okay, so I'm looking at the x values. So from negative 2 to 1, including those endpoints. Okay, and then to find the range, we're looking at the y values. So the y values, to find those, we're going to scan this y-axis from low to high. Okay, so start down here, there's nothing, 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 nothing. Then boom, right there I hit my first y value, which is at a y value, which is y values in orange here, that's at a y value of 0. And then I have y values, y values, y values, all the way up to 3. So my range here goes from 0 to 3, including those points because it has closed circles. Okay, at this point you should pause the video and try the next 4 on your own, finding domain and range from the graph. On B, for the domain, we go from left to right for the x-axis. So we're going along, then we hit our first x value here at negative 3, but it's got an open circle. So in interval notation, I would not include that value, so I'll put parentheses 0, and then we continue on out to this x value right here, which is at 2. That's the domain. And the range, we're looking at the y's that are a part of this graph. So we go from low to high. So there's nothing, nothing, nothing. Then right here, I finally hit my first y value, which is at y equals 1, not including 1, and then on up to just 2, including 2 for the closed dot. Then on part C, for the domain, we go from left to right. My first x value is right here at x equals negative 2, including it. Then I have a continuous line, so all of these x's are in the domain right up to this one at 1, not including 1 because I have an open circle. Now the range is slightly trickier here, but not too much. There's no y values, all the way up until 1. Okay, so my first y value is 1. I'm going to assume it actually goes through the point 0, 1. So it's a bit of an assumption here, but let's assume it in fact hits 1 and will include the y value of 1. Okay, right there. Then I actually have two of the same y's as I go on up. So as you imagine this vertical line moving up, see I'm touching 2 points at once, but that's fine. It's still a function because those are y values. Okay, now here I'll go from touching 2 points to only 1 point at a time, but I'm still covered. I still have y values, so those are still in the range all the way up to 5. And I have a closed circle there, so I'll include that point. Then on D, let's see, I have an arrow here. So as I'm imagining my vertical line going from left to right across here, this has an arrow. Okay, so that assumes all of these x's are in the domain. So all the way up from negative infinity up until 4 is in those values are all in my domain. So from negative infinity, and we always use a parenthesis with infinities, to 4, including 4. My range is the y value. So as I go low to high, my first y value I hit is right there, and that's at a y value of 0. So I'll go from 0. And then this goes, technically it does go up forever. I think it's hard to tell, but it doesn't quite look like it flattens off. I would say that those y values slowly go up forever and ever, so on up to infinity. And then last but not least, this is called a step function here. It looks like step. So the domain doesn't start until right here. That's the first x I hit as I go from left to right. And that's at x equals 1. And then I have a continuous line, and then at 2 it jumps up. Okay, it is a function because I don't have two closed dots. If this was a closed dot here and here, it would not be a function because I would have two different y values when x is 2. But one is an open circle, one's a closed circle. So this is good. All of these x's continue to have a single y all the way up to 4. Parentheses, we have an open circle at 4. And for the range, that's the y's. So as you imagine this vertical line, I'm going to try to imagine a flat, straight vertical line. There we go. Moving on up, I don't have anything in my range, nothing, until I get to this point, y equals 1. And I have a whole lot of points at y equals 1. Then there's nothing in between 1 and 2. So my next y value is 2. And there's nothing in between 2 and 3. So the next y value in my range is at 3. So my range is actually, I have to list the values, simply 1, 2, and 3. And that's it. And then you should also pause the video and try these two on your own. So for this function's domain and range, we have an arrow and an arrow. So as I go from left to right, everything is included. So from negative infinity all the way to positive infinity, or you can just say the set of all real numbers with the double bar R. And for my range, that's the y's. None of these y values are in the graph until I get right here to y equals 0. And then it looks like it goes up forever. So from 0 on up to infinity. And this is a fun one. So my x's, I go from left to right. Okay, I have an arrow here, so all these x's are in the domain, and then right here, at 1, the dashed line doesn't count. That's not part of the function. So 1 is actually has no y when x is 1. 1 is not in the domain, and then everything after that is. So I can think of two really decent ways to describe this domain. In interval notation, you go from negative infinity all the way right up to x equals 1, but not including 1, so we'll put a parenthesis, comma, or union sign. And then we pick right back up immediately after 1 on out to infinity. Or in set builder notation, you could say the set of all x such that x does not equal 1. Okay, and it's implied when you write that x is a real number. Always assume your variable is a real number unless stated otherwise. And the range is done similarly. You imagine that horizontal line, okay, coming across, and I have a single y value. All these y's from negative infinity on up to here are in the range. Okay, so for the range, we could go from negative infinity up to y equals 0 right there. But 0 is not in the range. This is an asymptote and the function never quite touches that x-axis. 0, and then after 0 we pick back up right here and go on up to infinity. Or similarly to this, you could say the set of all y such that y does not equal 0. Next, we're going to look at how to determine whether a graph is a function given its equation. Okay, so what we're going to do is look at the graphs of these problems right here. We're going to determine their domain and range, and then whether or not they are functions for these two problems and for these two right here. Okay, so on this first one, y equals x squared minus 4. You can plot this however you want. If you know about quadratics, you could plot it using that knowledge. If you don't know about quadratics and what shape this is going to have, I would recommend plotting a lot of points to graph this. Okay, y equals x squared is a parabola, and when you have a minus 4 after that, what's going to happen is it's going to shift 4 units down on that y-axis. Okay, so just write out a few little points here. This is for the first problem here. So when x is 0, 0 minus 4 is negative 4. It's going to go through 0, negative 4. When x is 1 or negative 1, either way, 1 squared is 1, minus 4 is negative 3, and negative 1 squared is also 1 minus 4, so it's also negative 3. So I have these 2 points, and then all the positive and negative values of x will have the same value of y. So, oops, that's not right. There we go. So when x is 2 or negative 2, that number squared is 4, minus 4 is 0. So that gives us our x-intercepts right there. Then when x is 3 or negative 3, that's 9, minus 4 is 5. Okay, this kind of shape is called a parabola. It's not really vertical there at the edges. It does continue to go kind of more out a little bit as it goes up. It's got a nice curve throughout the whole thing. So its domain is all real numbers. Okay, and you can kind of tell by looking at the graph, this does actually go out forever. But also just the idea that you can plug in any value of x here and you'll get a single y. I can take any x I want, square it, and subtract 4. So the domain is from negative infinity to infinity in interval notation, or all real numbers. And the range, those are the y's. That's easiest to figure out by just looking at the graph. That's part of the reason why we graphed it. So if I'm scanning the y-axis, remember, imagine that horizontal line here. And as I'm going up, okay, the first y value I hit is right there at negative 4. And then after that, all of those y values are covered. They're all in the range. So the range goes from negative 4 on up to infinity. Or you could say y is greater than or equal to negative 4. Or you could use step builder notation and get really fancy there. So is it a function? Well, does it pass the vertical line test? Now the way I drew it right there, it doesn't appear to. But in reality, like I said, it kind of goes more out like that. It does pass the vertical line test. For each x, there is exactly one y, which you can also tell just by plugging them in, because as you can tell as you make a chart here, for each x, you get exactly one y value. So yes, this is a function. Now on this one, I've got a little typo here. What I intended to actually type was y squared plus x equals 3. So we're going to change that. Reverse the variables there. Okay, so let's plot a few points for this one. Okay, so this one is actually a little bit easier to plot points by choosing the y first and then computing x. And you can kind of get an idea of that because it's easy to solve for x if you want to. You just put the y squared on the other side. Now normally you solve for y, you have y equals. I think it's just easier to compute numbers on this t-chart with this particular function by looking at it like this. So I'm going to choose a y value. How about, let's just start with 0 here. 0 squared is 0, so x equals 3 minus 0 or 3 when y is 0. Let's try when y is 1. 1 squared is 1, 3 minus 1 is 2. Let's try 2. When y is 2, I have 2 squared, that's 4. Is that right? Yeah, 2 squared is 4. 3 minus 4 is negative 1. Okay, what about y is 3? Let's try that. When y is 3, 3 squared is 9. 3 minus 9 is negative 6. That's going to be off my graph. So let's choose some negative values for y as well here. So let's try negative 1. Y is negative 1. Negative 1 squared is positive 1. So x is 3 minus 1 over 2. And let's see what that looks like. Then we may plot a few more points here. Let's get some tick marks going. You might have an idea that it's going to look similar to this problem over here, to that graph. Really, all that's happened is the x and the y are kind of reversed. Well, that's not the only thing that's happened, but that's essentially what's happened. One of them is squared and one of them is not. It's just the opposites in this case. Okay, plotting these points, we have 3, 0. We have 2, 1, negative 1, 2, negative 6, 3. Okay, it's got a parabolic shape there. But looks like the top half of a parabola that's kind of on its side. And then when I started picking numbers down here, when x is 2, y is negative 1. Ooh, right there you see a problem. Okay, let's pick a few more here. When x is, or actually let's choose y is, no, let's choose when x is right here. I think this is going to be a point just by symmetry. It should be. So when x is negative 1, let's look at this. What other value of y could x be? So I'm comparing it to this point right there. Okay, they both have an x value of negative 1. So if y was negative 2 all squared, that would be 4. 3 minus 4 is also negative 1. So that does work. So negative 2. That is a point on here. Negative 1, negative 2. So it is going to be symmetric, okay? It's the same as the top half here. And it looks like there's nothing out here. And if we tried to choose an x, like let's try to choose x as 4, we get 3. So actually, I've got to write this out. If we plug in 4 for x, so 4 equals 3 minus y squared. If I subtract 3 from both sides, I have 1 equals negative y squared. Multiply both sides by negative 1 to get negative 1 equals y squared. Well, that has no solution because no number squared will ever be negative. So there's nothing out here. So for the domain, let's use the vertical line here. As I'm moving across, well, the first thing you probably notice is that this is not a function because it's touching 2 points at once. Let's try that again. Here we go. Okay, it's touching 2 points at once just about everywhere. So not a function. It's domain because there's an arrow here. This does go out forever. It's going to go all the way from negative infinity up until x is 3. And we will include 3 there. For its range, that's the y. This does go down forever, and this does go up forever. So all real numbers or negative infinity to infinity is that domain. And like we said, it is not a function. Okay, next let's look at this one. Graph the function g of x equals the square root of 2x plus 4 minus 2. Okay, it's a radical function. We're going to, again, plot a few points here. So let's see, let's start with negative 2. Negative 2 for x times this 2 is negative 4. Plus 4 is 0, so I have the square root of 0 minus 2. The square root of 0 is 0. That's defined, it's fine. So I get negative 2. Let's try a larger number. When x is negative 1, I'll have negative 2. 1 times 2 is negative 2. Plus 4 is 2. It gives me a messy number. It's square root of 2 minus 2. You would need to approximate that on a calculator. Now I know square root of 2 is roughly 1.4. So this is roughly negative 0.6, which will be plenty good enough just for graphing purposes. Let's try when x is 0. I'll have square root of 4 is 2. Minus 2 is 0. I want to pick numbers that are easy to take the square root of here. So let's see if I did, actually that may be pretty hard to do. If x is 1, I'm going to have square root of 6. If x is 2, I'll have square root of 8. Yeah. Let's go ahead and graph it. We'll have to approximate a little bit. I'll go ahead and get my calculator going though. Now if I try to pick a number less than negative 2, let's try negative 3. I'd have square root of, this would be negative 6 plus 4 is negative 2. Square root of negative 2 minus 2. You can't take the square root of a negative number. It's undefined. So not a number, undefined, whatever you want to write, does not exist. Some people put D and E for does not exist. So any numbers less than negative 2, and that's the smallest because that's the one that gives you square root of 0, are not going to give you a defined y value here. Okay, let's get my calculator. Okay, and let's estimate some things real quick here. Let's just double check this one and see how close I was. So I'm going to do square root of 2, close the parentheses, minus 2 gives me, yeah, it's close to negative 0.6. Okay, then I want to do at least one more here. Let's go with when x is 3. And that would give me square root of 10 minus 2. Let's see what that is. There we go. Square root of 10 minus, oh, I wrote 3. I think I meant to write minus 2 is 1.16. Yeah, minus 2 there. Okay, so this graph starts at negative 2, negative 2, negative 1, negative 0.6, 0, 0, 3, 1.6. This is the basic shape of what's called a radical function. It kind of curves up. It goes up very, very slowly forever and ever, and there's just nothing out here. Because you can't take the square root of negative numbers, you end up with no graph out for that part. So the domain, the smallest x value I have is right here at negative 2. And then the x is going out forever to infinity. The range, also the smallest y value I have is right there, also at negative 2. And it does go up forever. It looks like it flattens off, but it really doesn't. It keeps going up. And yes, it definitely passes the vertical line test here. So that is a function. And let's look at one more. I want to graph the function y equals 4 over x. And note any restrictions on its domain. So we can make another little table of values here. Let's see, when x is, let's go negative. Actually, let's do negative 4, because that'll be a nice easy one to compute. Let's do negative 8 first. When x is negative 8, I'll have 4 divided by negative 8. That's negative 1/2. X is, I'm going to pick easy numbers here. So if x is negative 4, I'm going to have 4 divided by negative 4, which is negative 1. X is negative 2. 4 4 divided by negative 2 is negative 2. X is negative 1. 4 divided by negative 1 is negative 4. And I know from my experience, that I need to pick some fractions here. Okay, so I'm going to go with negative a half. Might have to write that one out here. So 4 divided by, let me write it out bigger up here. 4 divided by negative a half. In case you've forgotten how to handle a fraction inside of a denominator, what you do is you multiply the numerator times the reciprocal of that denominator, which means you flip it upside down. So when you flip that upside down, you get negative 2 over 1. 4 times negative 2 is negative 8. That's good. Notice if we try to plug in 0, you can't divide by 0. So 4 divided by 0 is undefined, so there's nothing there. Then let's pick it up again with a half. 4 divided by positive a half is the same here. It's just going to be positive 8. So 1, 4 divided by 1 is 4, and you get the picture. 2, 4 over 2 is 2. I think that's coming up. Running out of space here. Okay, so negative 8, comma, negative a half, very low, negative 4, negative 1, right about there, negative 2, negative 2, negative 1, oh, these are all supposed to be negative, hang on, whoops, let's try that again, negative 8, negative a half, negative 4, negative 1, negative 2, negative 2, negative 1, negative 4, negative a half, negative 8. Okay. The basic graph of a rational function. This is called a rational function because it's got a fraction. At x is 0, we're going to have an asymptote there. And then you can just follow the pattern and see that. That's the basic shape. Okay, we did another one like this earlier with the domain and range. So the domain is all the x's that you can plug in, everything except 0 here. Okay, I'm going to write it in set builder notation, say the set of all x, such that x does not equal 0. And for the range, the only range or y that we don't get is right there at 0. Set of all y, such that y does not equal 0. And is it a function? Yes, definitely a function. Because it's a vertical line test. Alright, and let's look at one more. This is just a simple application of function notation. So in this problem, a balloon has the shape of a sphere with a radius of 3 inches, and these formulas are given in function notation. V of r is how you read that, and S of r. So this is referring to volume, and S is referring to surface area of a balloon with radius r. So if we have a balloon with radius 3 and we want to find surface area and volume, we would need to find V of 3. 4/3 times pi times 3 cubed. Okay, 3 cubed, let's reverse this. You can always reverse the order of multiplication here. I'm going to write it as 4 times 3 cubed. I'm just putting the 3 cubed over by the 4, divided by 3 times pi. 3 cubed over 3, one of those 3's cancels, so we have 3 squared, which is 9, times 4 is 36. That's the exact volume. If you want to approximate, you need to use a calculator for that. So 36, oops. My calculator freezes quite often on here. Okay, so 36 times pi. The pi button is right there, so second, that thing, is 113.097. Generally, go out to many, many decimals unless you're certain you can round. So I'm going to go with 113.097 here. Inches, exact and approximate. And for the surface area, you would find S of 3, 4 pi times 3 squared, which is the same, coincidentally. This is the approximate sign right there. Kind of neat that they both have the same value, but the point is just that it's an example of an applied problem where you're using function notation. And that's it for this section.